Okay, so hello everyone. I am Ditobroto. So this is the first lecture on of the lecture series on quantum mechanics. So there's this tradition while taking any course or lecture in quantum mechanics that before starting you have to say that I don't understand quantum mechanics, because Richard Feynman has said that and Shankar has said that and stalwarts like that have said that. So I will also say the same thing, that I don't understand quantum mechanics. I know how to deal with quantum mechanics. I know how to use quantum mechanics. So my goal in this entire lecture series would be that by the end of it, you guys would be comfortable enough with quantum mechanics so that you can use in your physics endeavors in your life. Cool. Now, with this plot armor, I am also equipped that whenever I am getting a philosophical question, I can swipe that away very easily. But anyways, so here I have written something. It's incomplete, and we'll fill this up today. The agenda of today's lecture will be to fill this uh, puzzle and to understand what this says. So these are what are called the postulates of quantum mechanics. Any theory, to start any theory, you need a certain set of axioms, a certain set of postulates on which the theory can be based. Now, these are not the unique set of postulates on which you can start quantum mechanics. There, you can start quantum mechanics differently as well, but I feel for pedagogical reasons, this is a good point to start. So we'll start by filling up this crossword kind of thing, and then as we are filling this up, we'll try to understand as much as we can. Now, this first lecture was meant specifically to just cover these things, the basics of quantum mechanics. Uh, we'll go through the other things in the next lectures. I want you guys to sit with this quantum mechanics, sit with these postulates for some time. I want this to get soaked inside you well. Anyways, okay, so here we have a difference between classical and quantum mechanics. In classical mechanics, any state of a particle is governed by two quantities. What are they? You guys all know that. Great. So they are governed by position and momentum. And this position and momentum make up the 2D phase space, and every point in that phase space is a configuration of that the particle can take. You guys all know this, right? You came to the classical mechanics lecture series, right? So what we have, the quantum analog for it. The quantum analog is that the state of any particle is determined by a vector psi which resides in a Hilbert space. Now, first of all, we need to talk about what are these Hilbert spaces and what do we mean by some vectors being a part or being an element of this Hilbert space. So, to start about what are Hilbert spaces, I need a few I need a few definitions that I hope you guys know. If you guys don't know, then we can just go through them one by one. So, an Hilbert space is a vector space that is equipped with a complete inner product norm. The complete norm. So yeah, let's break it down piece by piece. So I said that a Hilbert space is a vector space. So by the way, are you guys where you guys taught vector spaces till now in your UMM 101? No. Okay, cool. How many of you guys know what a vector space is? Everyone? If you don't know, it's fine. You can start. Cool. Okay. So just for completeness, a vector space is a set on which we can define an operation. Okay, suppose you have define an operation addition. How is it defined? It's defined by this few properties. Suppose you apply it on two things. This is called the commutativity. You all know that, right? Similarly, you have associativity. you have distributivity, and you have the existence of an identity element. Now you can define an addition operation by like that. So a vector space is such that in which you have an addition operation such that if v1 and v2 are two elements of a vector space, then v1 plus v2 is also an element of that same vector space. This is the first property. And the second property is, if v1 is an element of vector space, this implies that any scalar multiple of that vector, lambda v1, is also a part of that vector space. Great. So we know what a vector space is. I said that for Hilbert spaces, we need vector spaces that are equipped with complete inner product. So we need to know what an inner product is. So an inner product is basically a bilinear map. It's a bilinear map of this form. It takes, suppose your space, your vector space or Hilbert space, whatever you call, suppose it's H. So it takes from H cross H, the Cartesian product of those two vector space, it takes from there to a field. Now this field can be real, this field can be complex. Generally in our discussion we'll be talking about complex fields. So an inner product is defined like this. Something that takes from this Cartesian product of spaces to a field. Now there are some properties of an inner product. I'm pretty sure you guys know this. I'll just list them out. Okay, tell me what does this mean? Anyone? Great, right. So an inner product is a map such that if you are taking the inner product of these two vectors, and if you are like inner product taking the swapping these two indices, it's just the complex conjugate of the other. This is the first property. The second property is called linearity. Now, suppose you have psi and you have some constant a times psi. Then linearity says that you will have a times. Now there's a catch here. This kind of a linearity only works for the second element and not for the first element. What we have for the first element is called the antilinearity. So suppose if you have a phi and psi, then you have tell me, is there any discussion about that? Okay, as I said that the amount content is less, so you guys can stop me anytime and discuss. Okay, cool. So in a lot of math literature, generally it is taken linear in the first entry and antilinear in the second entry. But here I have taken it like this because this corresponds directly to the Dirac notation that we have been talking about. In the Dirac notation, the second entry would be the kit and the first entry would be the bra. And for the if you just look at the inner product as a bracket, then you can see it will be linear in the first entry and antilinear in the second entry. Cool. Great. So this is the second property. The third property is called additivity. Now additivity is required because sometimes we might need to use the Cauchy-Schwarz inequality. This is called additivity. And the fourth point is called positive definiteness. Positive definiteness means that if we take the inner product with the same vector, this is always greater than equal to 0. And equality holds if both of them are 0. Like equality holds if psi is 0. So these are the properties of an inner product. Please try to understand that any bilinear function that takes two inputs, first input from H and second input from H, and maps it to a field. For us this field is C. That obeys these properties is an inner product. Any such function is an inner product. So if we have an inner product space, like if we have a vector space on which we can define an inner product, as you can see from this inner product, we can define this quantity. The inner product of a vector with itself. It's called the norm. Yeah. It is defined, this is called the norm. Okay. So it turns out that there are vector spaces like where you don't have an inner product, but you have a norm. Like the point is you can define a norm without using the definition from an inner product. There are other kinds of norms called operator norms, P norms, etc. This is also P norm. Anyways, so the point is there are other kind of norms that you can define. I would urge you to go back and read more about this. That norms that are defined without the use of an inner product. So the norm thing is a more general idea than inner product. But here we are, just for simplicity, we are talking about the norm that is being generated from an inner product. Cool? Great. Then we said that Hilbert space is a vector space. It has an inner product defined, inner product or norm, anything, but like for our discussion these will be interchangeable. And I said one more thing. Okay. Now this is a bit non-trivial. What do we mean by complete? By completeness, okay, before we come to completeness, I would need a few more things. So let's just skim over those things as well. Okay, cool. Do we know what linear independence means? How many? Everyone know? Great. So, do you know what dimension means?
Yes.
Suppose you have for this equation, if the only possible solution is, then we say that this is called linearly independent, right? Okay. Now this dimension is the largest number of linearly independent vectors that we can find out for any vector space. So if you have some vector space, you are told that okay, tell me what is the largest number of linearly independent vectors that you can find, and that is the dimension of a space. Now there might be vector spaces where there is no such largest number of vector spaces, and if such a largest number doesn't exist, we say that vector space is infinite dimensional. So dimension might be finite or infinite depending on that. So we know what linear independence is, we know what dimension is. Now orthonormality. Do you know what orthonormality is? Do you guys know? Okay. I'm asking this question every time and then I'm just going and explaining it again. So anyway. Okay, so phi A, phi B, if the inner product of them is 0 when B not equals A and 1 when B equals A, then we say these two to be orthonormal, right? Okay, so we know about linear independence, we know about orthonormality. What is the definition of a basis? A basis is an orthonormal set of vectors that are also complete, right? Is there any, do you guys know what a basis is? Great. So if we have an orthonormal set of vectors that are complete, then we can use them as a basis, right? So by using them as a basis, what I mean is, suppose you have any vector psi. Oh, I have already written. Suppose you have any vector psi. That vector psi can be written as a linear combination of these phi a's. And if you are able to denote, an unique sum of this kind for every psi, then this is called these phi a's are called to be a basis. Great, cool. Now tell me one thing. I just talked about infinite dimension, like dimension can be infinite, right? Now tell me, if I have an infinite dimensional vector space, then how do you define a sum like this? Is my question clear? This sum, I said that for a finite vector space, for a finite dimensional vector space, any vector can be expressed as a sum, a linear combination of its basis vectors. Now tell me what happens for an infinite dimensional vector space. Because it would be an infinite sum, right?
Yeah.
Now there's some problems with infinite sums. And I think by now you guys should know the problems, that whether the sum converges or not, that's a big question. You just can't write a sum. You need to know that if the sum converges or not. So the problem with infinite dimensional vector spaces, as we just discussed, is that this sum this may or may not converge. So to talk about this, we use so by this completeness, to understand this completeness, we would have to look at this thing. Suppose we are considering the partial sums, the nth partial sums. And if you have a sequence of these nth partial sums, if this sequence converges to some value in that space, then we can denote it using this limit Do you guys know all this, right? You guys have been taught this in UMA 1-1. This is a bit different than UMA 1-1 because these sequences are not just any sequences, these are called Cauchy sequences. And this is a norm. The one that you are dealing with in UMA 1-1 is a special kind of a norm. It's just the absolute value, right? Fine. So, the point is,
that is phi A, right?
yeah, sorry. Right. So we say the Cauchy we say the we say that the Cauchy sequence converges. We say this sequence converges if we can show the existence of a limit like this. Now this is important for sorry, just a second. Okay. Now the idea of this completeness is that all such sequences, all such Cauchy sequences that you can define in that space, all of them will indeed converge in that space. That is what is meant by completeness. Completeness means that all such sequences that you can define for vectors in a Hilbert space H, now all such sequences would indeed converge in that same vector, in that same vector space. If this criteria holds, then that vector space is called complete, Cauchy completeness. Now, why is this important? Like, why am I saying all this shit? This is important because this kind of a convergence helps us to denote these limits of this kind. And limits of things in a vector space is important because we might need our vectors we might need our states to be differentiable. There might be cases where we need to differentiate our states. So for the definition of differentiation, we need the limits to exist. We need things to be continuous, we need things to be differentiable, we need the limits to exist. So that's why we need this kind of, oh god, okay, that's why we need this kind of a definition of completeness. Okay, so having said that, any vector space that is equipped with the inner product and is complete is a Hilbert space. Now I will just say one or two, three things, and we can then start with actual quantum mechanics. Okay. One example of a Hilbert space is any finite dimensional vector space that in complex field that you are talking about. Suppose you have any Cn. This is an example of a Hilbert space. Why? Because you can define an inner product in this space like this. And hence the norm can be defined like this. This will be just the complex numbers that you are familiar with. So this is an example of a Hilbert space, any finite dimensional vector space. Okay. Now, a second example that we will be talking about is called L square. This is the infinite dimensional generalization of the same. So suppose you have a sequence of an infinite sequence of complex numbers. Suppose you have an infinite sequence of complex numbers like this, and you denote them as components of a vector, an infinite dimensional vector, right? So by the same prescription that we introduced in Cn, tell me what would be the norm for this L square? Right? And we need this norm to be finite. Otherwise, it won't be a Hilbert space. If we set this norm to be finite, we can say that any inner product like this, defined like this, will also be finite. Can anyone give me the justification for that? If we set this norm to be finite, then my claim is that any inner product like this will also be finite.
Lesser than this product.
Great, great. Cool. Then this is an example of a Hilbert space. Now this kind of a Hilbert space is basically the Hilbert space where suppose you have the energy of a particle in a box, the energies of a particle in a box. Those states, the eigenstates of a particle in a box, that forms a Hilbert space of this kind. Because it's infinite dimensional, but it's discrete. Right? There is one more kind of a space called the Lebesgue space. That's the last thing that I will be talking about. And as you can understand, that these things I am talking very loosely, very non-mathematically, because I just want you guys to just know it at the back of your mind. I don't. You guys can go back and read more about these things. Why is it called L square? I don't know. I don't know why it's called L square. Like genuinely, that's a good question. Okay. Do let me know if you understand, like get somewhere by L square. Okay. The third kind of space that we'll be talking about is it's also an infinite dimensional vector space, but it is a space of functions. So suppose you have functions like this. Then we can define the linear combinations of these functions like this for any on this space. If we define a norm of this kind, and if we require this norm to be finite, if we require that this norm will be less than infinity, again by Cauchy-Schwarz inequality, the inner product that will be defined like this. This will also be finite, right? Yeah, that's how we are defining the norm. Like for example, we define the norm to be a discrete sum of these things, right? Here in this space, these are all functions, and for these functions, we are defining the norm to be like this. It can be shown that this space for this kind of a norm is complete. So this is also a Hilbert space, an example of an Hilbert space. This is an infinite dimensional Hilbert space, but it is not discrete like the small L square, because it is a space of functions. So your wave functions in position space or momentum space, those wave functions will be a part of this Hilbert space. Okay, great. This is all that I have to say about Hilbert space. I think I just wanted to introduce Hilbert space just because we are telling about it in the postulates, but it's a very deep like topic in functional analysis, and if you are interested, you can just go ahead and learn about it. Yeah. So suppose you have uh, the energy eigenstates of a particle in a box or a harmonic oscillator potential or something like that. Those energy eigenstates are all part of the small L square. For small L square, it's the same thing. You just find the mod square of the state. Yeah, like those are wave functions, but I'm just saying that if you are can uh, can you tell me like Yeah, tell me.
Are there different values, the probability that the particle is found in that particular level?
Yeah, like when what you are talking about at the wave function when expressed in the position basis, that is indeed a part of the capital L square. But what I am talking about is the energy eigenvalues, energy eigenstates. Those energy eigenstates are forming small L square because those are discrete parts. Okay, cool. So fine. Let's get back to our postulates. So we said that in classical mechanics, any state is defined by x and t, but in quantum mechanics, we need this state vector psi, which is a part of this Hilbert space. Now there can be vectors that there can be two kinds of vectors in Hilbert spaces. Vectors that can be normalized to unity and vectors that cannot be normalized to unity. They can be only normalized to a Dirac delta function. Now, why this distinction? Why some vectors can be normalized to the unity and why some vectors cannot be normalized to unity, that we will be discussing soon. But the major idea is just you need this integral to be finite. Now, there are some states for which this integral won't be finite. For example, if you have a position eigenstate, a position eigenstate will be zero everywhere except for a particular point where the particle is. So that is kind of a Dirac delta function, and that is generally not normalizable to unity. Anyways, the point here is that there are proper vectors and improper vectors. Proper vectors are the ones that can be normalized to unity, and improper vectors are the ones that cannot be normalized to unity. Now, when I said that once you go from a classical point of view to the quantum point of view, you have this state that can indeed be an infinite dimensional state. One logical question that you could have asked me was that here you just have x and t, two variables. That is explaining the state of the system completely. But here we might need an infinite dimensional state. Why is it so? Why do we need an infinite dimensional state vector to explain the state in quantum mechanics? Why, when we can just use it from two variables in class? Any answers? Cool. We'll come back to it. I will give you the answer why we need an infinite dimensional case for quantum mechanics. Okay. As of now, take my word for it that a particle is represented by a vector psi in an Hilbert space. Now, if it is a vector, then we know that if psi and psi prime are two vectors in a state, so is alpha psi plus beta psi, right? So if psi is expressing the state of a particle and psi prime is also expressing another state of a particle, then alpha psi prime plus beta psi prime will also express a state of that same particle. Clear? Is everyone with me? Now this is called the principle of superposition. This principle of superposition is not something that is like unique to quantum mechanics. This is seen, for example, in classical mechanics as well. It is seen in electromagnetism as well. Suppose you have a solution, suppose you have a string like this. This is a solution to the string oscillation, and suppose this is also a solution to the string oscillation. Then in classical mechanics also we know that if these two are solutions to this string oscillation, then so is alpha f plus beta g. Right? But what is the difference between this and this? The major difference is this alpha F plus beta G is completely different in its characteristics from F or G. Like it will have a different wave shape, it will have a different kinetic energy, it will have complete different characteristics than either F or G. But in quantum mechanics, this state doesn't mean that it is having a completely different things. It has a different interpretation. The interpretation is, if you measure this state, this will sometimes show psi, sometimes show psi prime. Now, what do I mean by sometimes? Like, what do I mean by it will show sometimes to be a psi, sometimes to be a psi prime? We will define what this sometimes means, but for now, it's worth noting this difference between a classical superposition and a quantum superposition. Any questions? Good. We'll come to that. That is one of our postulates. What we mean by measurement. So we'll come to that. Okay. So this is more or less it about the first postulate. Now let's come to the second postulate. The second postulate states that every dynamical variable omega is a function of x and p. So in classical mechanics, if you are trying to find out any dynamical variable, be it say kinetic energy, anything, any force or any dynamical variable, that will be a function in terms of these 2 points, x and p, these 2 coordinates. The same thing has a different prescription in quantum mechanics. In quantum mechanics, these x and p are represented by Hermitian operators. And any other dynamical variable that is a function of omega xp will be given by another Hermitian operator omega that can be constructed like this. Did you guys get it? So this is the second postulate of the quantum mechanics. So the recipe, whenever you are trying to find out any dynamical variable in quantum mechanics, the general recipe would be, let's write it down once and for all. You have to construct a quantum operator like this. That is basically whatever classical variable you want to measure, you just change the x to the Hermitian operator for x, you just change the p to the Hermitian operator for p, and this will be your operator for that particular variable that you want to, dynamical variable that you want to measure. Huh? What is Hermitian? Do you know what is meant by this thing, complex conjugate of an operator? Uh-huh.
It is A-diagonal when A-diagonal is first of all unitary and also it's like this, right? Only then it's not.
Yeah.
Otherwise it's just A-diagonal.
Yeah. So a Hermitian operator is this. Do you know this? What this means? Okay. So this is called, okay, cool. So this is called the complex conjugate of a matrix. So you understand this, that the operators are determined by matrices, right? Expressed by matrices. So suppose you have a matrix and the elements can be complex numbers as well. So you take the complex conjugate of that matrix. So all those elements will be the complex conjugates of the numbers. Then you take a transpose. This is called a conjugate transfer. So this just means that you take the matrix, you do the complex conjugation of all those elements, and then you take a transposer. And if this is equal to the same matrix, then such a matrix is called Hermitian. Now there are some particular properties for which we need this omega to be Hermitian. We need omega to be Hermitian because the eigenvalues of Hermitian operators are always real. I hope you guys know what eigenvalues are. You know, right? Like there was a linear algebra talk before this. Great. So okay, is there any question, Ryan? Great. So this is the second first postulate of quantum mechanics. Let's get back to what we were talking about. Okay, any more questions right now? I'm going very slow. Any questions? You can discuss with me. It's fine. Yeah. So if I have an example of an operator in matrix form. Yeah, like I think we can talk about the spin operators. The spin operators are operators where you can explicitly find the matrix form of it. Yeah, the problem with position and momentum operators are those are infinite dimensional, right?
Why do these operators need to be Hermitian?
Yeah, these operators need to be Hermitian because we need the eigenvalues to be real. So the eigenvalue, as we will come to the discussion soon, the eigenvalue like when you are operating this operator on a state, the value that you are getting is the eigenvalue, and that eigenvalue is actually the real what is it called? The real variable that you are measuring. So any real measurement needs to be like any real life measurements need to be real, not complex, right?
But the fact that we're defining the real life measurement as the eigenvalue of that is just a
That is just a possible case. Yeah. So that's why we need the operators or the matrices to be Hermitian.
What is taking the adjoint of a vector function? And the just function. What is taking the adjoint of the function? The matrix I get the transpose and conjugate of the but when you have operator, what is taking the adjoint of an operator? It's not the same, but
It's the same thing, right?
it's the same thing. But
Like just the fact that you can express it as a matrix. The matrix might be finite, matrix might be infinite, but you can always express it as a matrix. In fact, the matrix like the elements of those matrix will be of this form. These are the elements of those matrices. Now you change x prime, you vary x prime, and then okay. So let me do one thing. Let me just write the postulate 3 as well, and then we can get back to the recipe that we were talking about. So the postulates 3, if you can see, it's written that if the particle is in a state given by x and p, the measurement of a variable omega will yield the value of this, and the state will be remain unaffected. That is for classical mechanics. What happens in quantum mechanics is if a particle is in its state psi and you apply a measurement operator like this, then it will yield one of the eigenvalues of omega. The probability and once this measurement is done, the state of the system will change from psi to that eigenvector. Read this statement once and try to understand what it says. So we are postulating it that whenever you are applying a operator like this on a state, the answer, the value that you will get is one of the eigenvalues of this operator. And the probability that you will get this particular eigenvalue is proportional to this quantity. And once you have made that measurement, the system will change from psi to omega, where omega is that eigenvector corresponding to this eigenvector.
Okay, that one also is just the graph that eigenvector of it, right?
Yes.
Yeah.
Exactly. So you find the inner product of the initial state with that particular eigenvalue, eigenstate, and the mod square of that inner product will give you the relative probability of finding that eigenvalue.
And the omega is the basis vector.
Omega?
It's like the basis vector.
No, omega is an eigenvector of this capital Omega.
Yeah.
So you have an operator. That operator can be diagonalized. That operator, once diagonalized, will have their eigenvalues and eigenvectors. I am postulating that whenever you are applying this operator on a state, the value that you will get will be an eigenvalue of the same operator. And after measurement, the state will collapse to that particular eigenvector that you just found. Is it clear? Is there any problem here? Because this is important.
So here the inner product is defined as a column matrix.
Yeah, just that. Any doubts? Anything?
Now regarding the second point, does being able to represent capital omega x and p as the combination of condition operators x, does that mean that any operator in quantum mechanics can be expressed as a condition operators x? Or
Great. So that is one of the complications that we'll be discussing. This prescription, this is not general. There are stuff where you can't just go through that recipe. So yeah, I'll state that recipe, and then we'll look at those complications, look at those cases where this recipe won't be applicable. Great question. Cool. So from postulates, again, is everyone okay? Like, is everyone understanding? Because there's no point otherwise. Fine. So suppose you have the operator like this, and you construct this quantum operator just by changing the position to the position operators, the momentum to the momentum operators, and you have this quantum operator. What should be the second step? Second step would be to diagonalize it and to find out the eigenvectors and the eigenvalues. Now, once you have the eigenvectors, you can always construct an orthonormal set of eigenvectors. Like, you can always find an orthonormal set of eigenvectors. So you construct an operator, you find an orthonormal set of eigenvectors for those operators and those eigenvalues, and then you expand the state that you have, the state of the particle. You expand that state as a linear combination of those orthonormal set of eigenvectors. Now I want to stress the point that these eigenvectors requiring to be orthonormal is important. Why? Because my next step is to denote psi as a linear combination like this. And to denote psi as a linear combination like this, we need this to be a basis of that eigenspace. Right? We need this to be a basis of that vector space. And this will be a basis of that vector space if and only if those are orthonormal. Right? So we have an operator in classical mechanics. We change all the x's to the x operators, the p's to the p operators, and we construct the quantum operator. Now we take the quantum operator, we find the eigenvalues, and we find an orthonormal set of eigenvectors for that quantum operator. Then we express the state psi that we have, the initial state psi of the particle that we have, as a linear combination of this orthonormal set of eigenvectors. Once you are done with this, then the probability of finding the state, in some eigenvalue omega, the probability of obtaining some eigenvalue omega is given by these can also be written in a different way. Suppose if I introduce an operator like this is called the projection operator. If I introduce an operator like this, this thing is nothing but did everyone understand this step? Is there any doubt? You can ask, you can genuinely ask. Did everyone understand from this step to this step? This is a complex number, right? This is an inner product. Inner product, we define the inner product taking from H cross H to C. So this inner product will take from H cross H to C. So this is a complex number. Now the absolute value of a complex number is given by its complex conjugate times itself. Now this is itself and this is the complex number. Clear? Is everything okay? Good. Now if we write like this, you can see this is the projection operator, the projection matrix that we just defined. So we can substitute this with right. So the alternate definition is the probability. When you have a state, the probability that after measurement, the state will give you a value omega is proportional to this thing. Please note what I am saying properly. I am saying the probability that after measurement you will get a value omega is this. So this is the probability that you are calculating on the state before measurement. After you have actually measured, you will get one of the eigenvalues. This is a point of confusion for a lot of people. Yes. P omega is just something that I defined. I defined this as the projection operator. Projection operator means it takes any given state, it finds the projection of any given state to that state. For example, suppose you have three eigenstates like this, like three bases, and suppose you have a state like this, right? Now this projection operator on when applied on suppose if you are talking about the projection operator for omega 1, that will be given by, right? Like this is the definition of the projection operator that I am just saying. Now suppose you apply this projection operator on this state side. Tell me what it gives. This is omega 1 times omega 1 sine. Right? This is like the projection of this state on this axis. Even think of it like that. And this is this. Is it clear? Suppose you applied this, then what would have happened? This would be the projection of psi on this axis, and this would be this. So this is the normal projection that you learn in vectors. That if you have a vector, you take the projection of that vector in any axis. Component. So projection operator is something that takes the component of a state in one of the eigen bases. So are people okay with this? The recipe that we just discussed? Yeah.
How do you know that the eigenvectors are going to be all?
Because
No. Yeah.
That's
So
a guarantee.
no, you can always construct a set of orthonormal eigenvectors. Like there are orthonormalization techniques that you can use to.
In normal,
The eigenvectors are fixed. We can't change them around.
No, eigenvectors are not.
linear combination of eigenvectors is not eigenvector. It's not.
only if the eigenvector is okay, question. Like if you have some operation, and if you eigenvectors are not normal to each other, orthonormal to each other, you can obviously normalize them. How do you ensure that their inner products are zero if they're different in one of the other?
Why?
Because we want an orthonormal set of eigenvectors. If we apply this on the eigenvectors, the resulting vectors won't be eigenvectors.
No, they would. That's the. Huh?
Why will they be? No, they will be orthonormal. They will be an orthonormal basis, but not necessarily they will be eigenvectors. So for them to be eigenvectors, you need that linear combination of them is also an eigenvector, which is just
Can you explain? Can you tell me one?
like
Here we'll be taking a linear combination of all of the bases
weighted by something.
to get orthonormal vectors.
Yeah.
But those aren't eigenvectors anymore. Taking a linear combination of eigenvectors won't give eigenvectors.
Yeah, because eigenvector does not need to be the same eigenvector.
No, like suppose you have a matrix and you are diagonalizing it. So when you are diagonalizing it, diagonalization just means to find. It's a technique to find out the eigenvalues and eigenvalues. So when you are diagonalizing it, the choice of eigenvalues are fixed. Like you find that the eigenvalues are this. But when you construct the eigenvectors, those eigenvectors construction is arbitrary to some extent, right?
Only up to scale.
Yeah.
No, linear combination of two
Linear
eigenvectors.
combination, like
I'll write an example.
Let's say there are psi1 and psi2.
Yeah.
So h of psi1 plus a psi1 plus the psi1 plus psi2.
Just write it.
Just a second. Just
That will be a psi1 plus b psi2.
right. So
That is an
Yeah.
that is a psi1 plus b psi2.
Yeah, A and B are the eigenvalues. But you can't write it as a constant times I1 plus I2, right? Unless A equals 0.
right.
So the eigenvectors will have to be orthonormal in themselves, and they are, I think,
I think because of condition. Yeah.
in linear algebra.
Yeah. Yeah, you're right. You're right. The eigenvectors of a Hermitian matrix are orthogonal. Okay. Yeah, probably. Yeah, probably.
One more thing. Because you're working with infinite dimensional vector spaces, there are, what happens if your eigenvectors are not normalized?
Yeah. So that's one of the points that I was going to discuss. So
We had an example of that, right? The momentum.
yeah, that's one of the points that I was going to discuss. That in general, when we are talking about this normalization, it's not necessary that it will always be normalizable. It might be not be normalizable to unity. It might be normalizable to a Dirac delta function for improper vectors like that. So what you are talking about is exactly that case.
Normalizable to their
Dirac delta function. Well, we'll go into that.
What is that?
Everywhere 0, but at a point.
Yes. So it's 0 everywhere, but except for a particular point. Those
Area is
yes, the entire area when you take the integral over the entire space, that is integral. So those kind of vectors are improper vectors. Those vectors won't we won't be able to normalize them using this prescription, like this prescription.
So, like, the particle can exist in a state which is a linear combination, any linear combination of the eigenstate. So, but when we measure it, we will always get one of the eigenstates. So, what does it mean for, how do we know that there is a state, like what is the significance of there being a state which, if one measured, it only leads to one of the eigenstates, but it's itself not identical to any of the eigenstates.
I didn't get the question.
Like, what does it mean for us to have a linear combination of the eigenstates when measuring it leads to only one of the eigenstates?
Yeah, because unless and until you are measuring it, you still have the probability, right? So suppose you have some state, you have a black box. Unless and until you are measuring it, you know that. Okay. So you have this state, and you want to measure this state using this operator omega. Now you know what are the eigenvalues of this omega, and you also know what are the eigenvectors of this omega. Right? So before measurement, you want to say that what is the probability that after measurement I will get this some eigen omega. That is given by that side. But as soon as you measure it, it will collapse to any one of those eigenvalues. So what happens is, suppose you have a system psi and you make n copies of them, right? If the probability of getting psi 1 is 1 by 3, then once you do the measurement, so there are n copies of this states psi. You are doing measurements on all of them. You are measuring this. N by 3 of the times you will get omega 1. And 2n by 3 times you will get omega 2. So this is what is meant by this probabilistic interpretation. Huh?
Just a doubt, if you have a single and you measure it.
Yeah.
And you measure.
If we have a
If you have a single system and you measure it, and our collapse with one of the things. Now if you measure it again, you get the same answer.
yeah.
Because our state
Yes,
is
yes, exactly. Okay, just a second. I think it will, if you if you want to discuss something, it will be great if you discuss with me. Otherwise,
We were trying to find an example of that case where
No, I
we
can't
can't normalize.
have a free particle.
yeah, exactly. The free particle or the plane wave solutions of momentum. All of those are examples of states. Like if you have a state like this. If you have a state like this, you can see that it is not normalized. Why? Because when you will be finding mod psi square, this thing will be gone. So you will be just left with this. I think we can cover these things in the next lecture as well. But yeah, the point is there are states that are not normalizable to unity, that can only be normalized to Dirac delta function. Anyways, did you understand the point that I did you get the answer to your question?
Yeah. So does this state psi have a physical significance?
Yes. The state psi contains all the information about the state system. Suppose you have a dynamical variable omega. Suppose you have a dynamical variable lambda. Suppose you have a dynamical variable gamma. For all these dynamical variables, you can express the state as a linear combination of the eigenvectors of this or eigenvectors of this, and that will give you the probabilistic amplitudes of all of those things. So no matter what dynamical variable you choose to measure the state with, all the information about the state is encoded in that psi. You need to decode that psi with a particular operator to get the eigenvalues of that dynamical variable. Yes, I think you had a question. Yes. Normalization can norm can be infinite. I said for improper vectors it might not be normal. I didn't say the norm to be infinite. That's a different thing. The norm won't be infinite. In fact, for an Hilbert space to be defined, we need the norm to be finite, right? We discussed in the beginning.
If the norm is not infinite, then they should always be normalizable to unity.
No? Oh, right. Sorry. Yeah. Right. Right. Yeah, you're right.
If you measure an eigenstate and you get some value, you're saying that eigenstate is not in that original state, right? You're saying it is collapsed.
Yeah.
So if we try measuring it again, will we only get the thing that we have measured?
Exactly. If you measure it again with the same variable, you will only get that. If you measure that state with some other variable, you will get something else. That we'll also discuss. If you have a state, you measure it with some variable omega, it collapses to one of the eigenvectors of that omega. Now if you measure this collapsed state with some other dynamical variable lambda, then you will get something else. Then you will get one of the eigenvectors of lambda. And how will you get that? It will get that like this. So you have psi, you operate omega on this, you get some eigenvector of omega. Now you operate another operator lambda on it, you get lambda. How? You basically this. And what is the probability that you will get any how to find out the probability that you will get any vector lambda I? You can find that out by expressing omega as a linear combination of this lambda I. So if you express omega if you express omega like this, then this will give me the probability that this will be lambda. Yeah.
You showed us the example of a e to the I k x, for example. That is not normalizable to either unity or denominator.
That is
How will we normalize that? And its norm is infinity.
no. It is not. I think it is normalizable to do that.
Its norm is equal to oh, it's just a square. How? Just a. But the integral is not.
Integral. There's an integral. There's an integral as well.
Okay.
The norm is
No, it does not be.
That's not a wave function.
No,
That's not a wave function.
that is.
Yeah.
That is a wave function. Hmm.
Omega and lambda.
Hmm.
Can we do it in position moment?
Yes.
But then every time you measure x and t, you keep getting the same value. So you know the exact x and t.
Nah, that's the thing. So when you are measuring with omega here, you know with certainty about omega, but you don't know anything about lambda eigenvalues of this state. Similarly, क्या हुआ? कुछ हुआ क्या?
what is a dynamical variable?
हाँ?
Dynamical variable.
Dynamical variable is any dynamical physical quantity, kinetic energy, potential energy, force, anything. Yeah. Is there any problem? Am I saying something wrong? I'm sorry.
I didn't know what a dynamical.
Okay, cool.
Can I ask this?
Just a, yeah. So suppose you are measuring it with omega, it collapses to this state. You know nothing about lambda. Similarly, once you are measuring it with lambda and it is collapsing to one of the states lambda I, you know nothing about omega.
So once you take a measurement, then I thought once you take a measurement, it stays in that state.
No, it will stay in this state if you are again measuring with the same operator. No?
Okay, so then if you measure the different operator,
Yeah, because if you are measuring with a different operator, you need to express that state as a linear combination like this, and then the probability will be given by like this.
like then again if you measure omega, then you get a different value.
Does that linear combination of lambda depend on the twist wave function?
Yes.
Yeah, does that depend on psi? It does.
Once you have done this measurement process,
So if there's another completely different wave function.
yeah, exactly. Omega can be thought of a completely different thing. That is just the eigenvector of this omega. Two measurements at the same time? No, I don't think so. We can do two measurements.
If you have two operators, whose commutator is 0.
Yeah.
So you can
Okay, so I didn't want to come to that point. So this prescription, this happens for things, two non-commutating observables, omega and lambda. I will come to that point, but like the questions are taking so much time. That's the point. Yeah, I have now. You guys can ask those questions, but whatever you are asking are all covered in the note. Yeah. If you guys have any other questions, you can like for the time being. Then we can start.
You can't represent time as a function of momentum.
It's just a parameter. Time is not a dynamical variable. Frequency? No, it's not a dynamical variable. It's a parameter. Both time and frequencies are parameters.
The frequency of quantity you can't represent as a function.
Yeah, you can measure anything in frequency space as well as you can measure it in time space. It's a parameter, but it's not a dynamical variable. Okay, cool. So this recipe that I was talking about for doing quantum mechanics, for finding the dynamical things for anything, this has before going to the complications, I have to tell you about some points. First thing, that we are only talking about probabilistic things, that the probability of getting omega is this. We are not saying definitely that this will be done. This definiteness comes once and only if and only if we have actually performed the measurement. Before performing the measurement, we don't know definitely what the state of the system is. We can just give probabilistic concepts that, okay, I will measure this state with this much probability. Is that clear? Okay. One more thing is, the fact that omega being real ensures that you have real. Omega being Hermitian gives you this assurance that eigenvalues will be real and eigenvectors can be orthonormal. So this is also a point that we need to take care of. And the third point is the one that we were discussing till now, that this is a relative probability. If you can see, the probability is directly proportional to this. How to find out the absolute probability? That, okay, I have this state, I make this measurement, what is the probability of getting this particular value? What is that? So, yes, exactly. So you can understand that this will just be the relative probability divided by the sum of all such probabilities. I think this is pretty obvious why this is so, because the sum has to be, the probability has to add up to unity, right? So this is the reason. So you could have done this, or you could have from the beginning started with normalized vectors like this. If you had started with normalized vectors like this, then the probability can be directly written like again, a point of caution, these is only possible for proper vectors that can be normalized to unity. For improper vectors, I haven't said anything. They can't be done like this. Like improper vectors means vectors for which you can't find this. Why you can't find this? Because this thing, this is the norm, right? And for improper vectors, this norm might not be a finite number. This might diverge. So for them, if it is not a finite number, you can divide it and normalize the state like this, just like we were discussing that. But if it is not finite, then you can't do that. And those kind of vectors are improper vectors, and they can't be normalized. Like normalized to unity, they can be normalized to Dirac delta function. Okay, cool. Now tell me one thing. With this prescription that you have, tell me one thing. If my initial state was itself an eigen vector of the dynamical variable that I want to measure, then what is the probability? Did you get my question? My initial state psi is itself an eigenvector of omega. This is an eigenvector of omega. Then what is the probability of getting omega A? Exactly. 1. It is pretty obvious, right? You have the point of this probabilistic thing, the point of this statistical interpretation, that okay, this might be this eigenvalue with this much weight, this eigenvalue with this much weight. That all comes from the fact that the psi can be written as a linear superposition of all the eigenbases. If it is just one of them, then obvious it will be 1. You can even plug it in this thing. Yeah. E of omega was just what was it? Yeah, right. Omega psi Something like this, right? Something like this, right? So if you just plug that omega psi equals to omega, this will just go to 1. So if you remember, I told you in the beginning that in quantum mechanics, linear superposition has a different meaning than in normal classical mechanics. I said that any linear superposition like this will admit to psi sometimes and admit to psi prime some other times. Now I will define this, what sometimes means. What sometimes means is, we'll just go back to the same recipe that we talked about. Suppose we have this, okay, this is not normalized, so let's just normalize it first time. Let's just normalize the psi at the first place. So suppose tell me what we have to do for normalizing it. Is this normalized now? Yeah, these are orthogonal. These are orthogonal, yes. These are eigenvectors, right? These are eigenvectors of omega. I am using the same notation everywhere. These are the eigenvectors of omega. So if you have an initial superposed state like this, and you want to find out the probability, that what is the probability of getting this value. Tell me what will be the probability of getting that value. You have on the board everything that you need to find. Almost correct. Fair enough? Cool. Similarly, probability for omega 2 will be trivially these two add to unity because these are the only two. Cool. Okay. So again, because we are talking about the superposition state, I want to tell you that this the peculiarity of quantum mechanics is that this superposition state is very different than alpha f plus beta g. In a normal classical string oscillation thing or something. In a classical string oscillation, alpha f plus beta g is very different than f or g. But here alpha psi plus beta psi prime is a linear combination of psi and psi prime. That means something else that we just discussed. Cool? Fine. Now that we have talked about this recipe and we have talked about how to find out the probabilities for a superposed state, how to find out the probability if it is an eigenvector of the same thing, I need to talk about some complications of this recipe. Now these complications are some of the questions that you guys were asking, and it's great that you guys were asking these questions. Now tell me one thing, if my classical dynamical variable is something like this, or some function like this, some function of xp, then what do you do for this? Do you write it as xp or do you write it as px? Because these are matrices, they might not commute. So I said in this prescription, the first point is that you change the x's to x and the p to p in omega. But if it is something like this, what do you do? So there's no clear answer to it. What you can do is you can do a symmetrization like this. You can do something like this, or whether it will be this or this will be given by experiments and other intuitive discussions. Like you can't theoretically just say that it will be xp or px. Like there's no bias towards xp or px. experiments of that particular dynamical variable will give you that whether it will be xp or px. Is there a question? Yeah, exactly. That's why I'm telling these are the complications of the recipe that I said. These are the things that these are the problems.
Okay, so we don't know which of the three it is. Basically.
No, for most cases this is the thing that we use.
Just take it.
Yeah, like we don't know whether xp will come or px will come. So what we do is if we have a product of x and p in classical x and p, we substitute with a symmetric product like that because we don't know what should come first. Like
And is there some kind of places where you have a product but a weighted
it might. I don't know of an example actually, but it might.
1/3 XP?
It might. Yes. Can you please? Yeah. What is XP measuring? Yeah, like that's what I'm saying. Like you can define a dynamical variable anyhow. Say this is a dynamical variable. I don't know why, but I want to find out the product of position and momentum of any part. I want to. So that is a dynamical variable in classical mechanics that I define. Yeah, I am defining that if my dynamical variable is given by this x in classical mechanics, then how do you go through this recipe from classical to quantum? This recipe is basically how you go from classical to quantum, right? You take the dynamical variable, you change this, you go to the quantum operator, you find its eigenvalues, eigenvectors. I've been repeating this like n number of times now. And then you find out the probabilities of getting a particular value. Now this is a complication. Did people understand why this complication arises at the first place? Huh?
Usually what we working with three vectors.
We usually
Vectors.
Ah.
Vectors. So like usually this is like a
yeah, exactly. Can you think of a dynamical variable that uses this or any function of this? No, right? Huh? Action.
So maybe in this case we actually know what
Right. Exactly. We know because we can change the Hamiltonian directly. There we can change. Yeah, you were right. Action can be an example. So this is a complication, right? The second complication is in this entire thing till now, whatever I have said, I have considered one thing silently that none of you guys have pointed out is that the spectrum of the operator is non-degenerate. Like all the eigenvalues are distinct. That I have what should I say? That I have assumed throughout. What is the problem? Right? Exactly. We'll talk about the problem. So
How do you find which eigenvector it is?
exactly. So suppose you have omega 1, suppose you have omega 2, both of them have the same eigenvalue omega. It's fine. On measurement, you will get omega with some probability. But we don't know which state it is. And we don't know how to find out the probability. We don't know how to find out the probability omega
I think that is a good one.
to get this eigenvalue. Like till now, we will know after this, but till now we don't know how to get this omega. Right? Because this formula, if you remember, use this thing. What do I put in here? Do I put omega 1 or do I put omega 2?
Will they give us names?
You can add the probability.
Correct.
Project in the plane.
Exactly. So we project on that plane. Exactly. Again, let's get back to our favorite picture that we have been using all this while. You have omega 1, you have omega 2, you have omega 3. And okay, so these two are, say, degenerate, like having the same eigenvalue. So you can't distinguish omega 2 and omega this like this. So let's do this thing. So I'm saying omega 2 equals to omega 3 equals to omega. Cool. So this is the value. This is the eigenvalue. Now for this eigenvalue, these two eigenstates, how do I distinguish these two eigenstates? Let me just add one more new label just for the sake of it to distinguish these two. Fine. Now you have a state like this. And initially when we were trying to find out the probability of finding, okay, let me just draw that picture as well, just to give you a difference. This was omega 1, this was omega 2, this was omega 3, and this was my sign. When I was asking you what is the probability of getting a value omega 2 on measurement, what you were doing, you were projecting omega, this psi on omega 2, and you were calculating this component. This component was just omega 2 times psi. Cool. And for this projection operation, we also made this projector. Right. Here, if I am saying that okay, you have this state psi and you perform a measurement, and I ask you what is the probability that you get the value to be omega, then what you need to do is you need to make a projection on this plane, because now you don't know this is the eigenstate or this is the eigenstate. Actually, this would be a superposition of these two eigenstates.
Yeah.
Right. So if you have to project this on this plane, I propose that you need a projector like this. Understandable? Yes.
How do we know that this is the right way to get the problem? Why can't we get the two probabilities and add them? So that is in this.
Because it's just a vector in that plane.
Why?
It is the vector.
Why?
Take the dot. We take the product like what do you find? The product of that along omega and the product of that along omega. So it's just the point of the why?
How do you measure? Because all the probabilities are one thing.
Yeah. Is there someone else asked? This is the probability that you will get. If you just apply the, this will, did you understand?
Yes, sir.
Did you understand? So this is the projector operator that you have to define to get a value in case of a degenerate spectrum. So this was the second second complication that we talked about. Now the third complication is say the spectrum is continuous instead of discrete. What I mean by continuous spectrum is, okay, by the way, you understand what is meant by a continuous spectrum, right? So the eigenvalues need not be discrete points like this. Like it might not be lambda 1, lambda 2, lambda 3. Lambda can take any real value. So say, so that is a continuous spectrum. So say the spectrum is continuous instead of discrete. So we talked about how to resolve the case if the spectrum is degenerate. Now we'll talk how to resolve if the spectrum is continuous.
Space that we are using for all our states. What is the how many eigenvalues can you use a space like that? Can they have obviously they can have countably infinite? Can they be uncountable?
Yes, they can be uncountably infinite. That's the point that I'm trying to make. They can be uncountably infinite. Like for example, say if you have a position operator, what will be the eigenvalues of the position operator? The eigenvalues of the position operator will be every position that a particle can take. That will be countably infinite. Right? So yeah, exactly. That's sorry. Yeah, that will be uncountably infinite. So those are the cases where my spectrum will be continuous spectrum instead of a discrete spectrum. So in case of a continuous spectrum, what we do is we write psi as an integral Now this is not a very straightforward generalization from the sum to this thing. Why? Because when we were finding the sum, we were finding this. We are finding it at discrete points. But for this generalization to take place,
Isn't that omega? Okay.
which one? Yeah, sorry. Yeah, this is omega. Right. So for this,
On the right.
Yeah, I see.
oh right, yeah. Sorry. Yeah. For this to take place, you need these to be a smooth function as omega is changing. Did you guys realize, like, see that? As you are changing omega, this needs to be a smooth function. Exactly. So this is often denoted like this, and it's called the wave function in omega space. So the idea is, if you have this state resides in Hilbert space. This omega space, lambda space, tau space, whatever you construct for whatever physical variable that you are taking, that space has no relation with this Hilbert space. This is just a one-dimensional space that you are finding, and at each point that this omega can take, you have some value of psi. I'm just saying that instead of making this discrete, you make them continuous.
And this is just a prediction of that omega.
Yes, exactly. So I'm saying that you can always find a continuous function like this. And this continuous function is called the wave function in that space, omega space. A very, very obvious thing that you have been using everywhere is this wave function in position space. That is an example of the same thing, because position is a continuous variable. So you have a one-dimensional position space that is continuous. At each point you define psi of x as this thing, and then you find out the function psi of x.
I think it's the notation. Like in the bracket we have x and psi.
Yes.
What does it?
What? This one? This one?
Yeah, omega.
Projection of that.
What
That's
is
the-
omega? Like what are these omegas? I think the question.
Omegas are the values that these omegas are the values that this can take. Now say this has a continuous spectrum. So this omega can take every value. Like instead of taking
Vectors of capital.
yeah.
in
Yes. 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 That's why I define L square, right? Capital L square. Did you get it? Okay, tell me. Huh?
Capital S square is the function from R to C.
Yeah, yeah. Square integrable functions. The
Square itself.
space of all square integrable functions. Yes.
The psi of omega is like expressing psi in omega. So can we not think of psi itself as a function? Right? Because the functions in the set of functions in the vector space. Can't we think of the get psi as function itself? As a thought.
But that function will be in the Hilbert space, right? Here, this is a function in this space. This is a function in X space. Do you get what I'm like? Do you get the answer?
Space of all of the functions that take x and has been.
Yeah, that will be the Hilbert space. Yes, that's true. That's true. That's true. Okay, answer me this thing. For this kind of a continuous variable, can we just assign this thing that okay, the probability of finding thing at this. Can we say this?
for 1 omega rho, we need to find it for a range of
Exactly. So for the discrete case, we could just say that okay, the relative probability of finding the state at omega 1 or omega I was this thing. But for continuous case, we can't say that because this is now a probability density. This is now the probability of finding the state in a from suppose you have omega plus d omega. The probability of finding the state in this is this. So what do we have to find to get the entire probability from?
An integral.
Exactly. So in fact, you can actually perform this integral and see that this is actually turning to unity. Suppose you have p of omega d omega integral. So that will just be sorry. Yeah, is this fine? Till now? Now again, I'll be using the same thing. This is a complex number. You are finding the mod square of that complex number, so it's just we have done this before. We have done this step before. I am going through these things so slowly, so step by step because this is the first time you guys are doing all this. So you have done this before, right? Like in the beginning. And this is identity. The completeness. Cool. This is identity. The projection matrix that you are talking about. Yeah, so you are taking the integral over the entire space. Na? So that will be identity. Okay, let me do this.
With the identity operator omega.
Yes, exactly. This is identity, right? This you agree? Like you should agree this because this was taught in linear algebra. This was taught in linear algebra.
Yes.
So this is identity, right?
Yes.
So this is also identity. Cool.
There is one more thing I can't understand. Like omegas are like vectors, right? So what is d omega? How can we integrate over it?
Omega is not the vector. The kth omega is a vector. Omega is a real number. That's what I have been saying. That you take omega, you define a space, you define a one-dimensional space. Just like in omega x, you are defining a one-dimensional space, that is position. And you find the wave function in that space.
Get omega is a vector which corresponds to that.
Exactly. So this is indeed one. That's what I'm trying to say, that okay, this you can actually think about a probability like a probability density. Probability density probability density that your states on measurement will give a probability between omega and will give a value between omega and d omega. Till now, is there a question? Like, is there something that you are not able to understand at all?
In this thing, the omega to omega 3, taking the projection on the plane, you mean omega 2 and 3 is equal to 1 and 2?
Where?
Like, omega 2 is equal to omega 3 is equal to omega.
Oh, sorry. Yes.
So if we had like 3 or 4 degenerate eigenstates, then we just write the same.
Exactly. So here it is a 2D space, right? Here it is a 2D space. Suppose you have, say, 3 degenerate eigenvectors. Suppose you have 3 degenerate eigenvectors. You have this, you have this, you have this. So this is a 4-dimensional space, and then you have a psi. You take the projection of that psi in this 3-dimensional subspace. The projection of that psi in that 3-dimensional subspace will give you the probability of getting this omega. Is that clear?
Yeah.
So I started with this question that I asked you, that in postulate 1, you just need, in classical mechanics, you just needed x and p. But here you need infinite dimensional vector. I think now you can be able to understand. Right? Because to write the state for x, for capital X, even to write that state, you need infinite dimensional vector, right? Because you need to find these things for every position. You need to find xi for every position. Am I making sense? Huh? Am I making some sense? You have position. These can take continuous values from 0 to minus infinity to infinity. To write this psi, as we saw, we need these things. And these things we need for every omega.
Just
And-
one question.
yeah.
For the classical case also, we kind of say that this is true that anything has a value for each x, but as it's like classical position, for only one x it has like one value and everything else is just 0. So we can consider that as one variable. We don't need information for all.
Yeah, we don't need information, exactly. But for quantum mechanics, the description is such, the algorithm is such that you need the entire depiction, because this psi can technically, there is a probability of finding this psi at every position. But in classical mechanics, that's not the case. That is at a definite position and a definite moment.
So can we say classical is basically an approximation where we are assuming that the particle is at only one of the positions? so we can remove a lot of the excess
Exactly.
information, which is
Exactly.
all of the other things.
Exactly. In fact, there's a I won't be discussing it, at least not today. There's a thing where how you can go from quantum to classical. It's called the classical limit. The classical limit. So you take a classical limit and you go from quantum mechanics to classical limit. Quantum mechanics is more fundamental in the sense that the state is in principle can be at every place. Probabilistically, there is a probability of finding that state at every place. Now, the last point of this discussion that I wanted to say. So there is one more complication that we didn't talk about, and I think one of you pointed this out.
The eigenfunction can't be normal. Eigenvector can't be normal.
No, eigenvectors would be normal for Hermitian. That's not the point. The point is this entire prescription lies heavily on the fact that you have this. What if we have some quantum variable that doesn't have a classical analog? Spin. Exactly. Spin is an example of a quantum variable that doesn't have a classical analog. Spin in the sense, spin angular momentum. Spin angular momentum is not related to its motional angular momentum. So that is something purely quantum mechanical that doesn't have a classical analog. So how do we construct a spin operator through these postulates? The answer is we can't. We can't. There's a complete different way of defining spin from semi-classical approaches and from intuition. This algorithm can't work for operators, quantum operators that are not directly derivable from classical elements. But the good thing is the quantum operators like that are very limited. Like spin is one of the examples that you can just think of in your mind. I don't think there is any, at least I don't remember any other example. There might be other examples, I don't remember any other example.
Those charge and that kind of thing.
I think we can have this discussion at the end of the class. Okay. So till now, what you have said, there's this sign that resides in a Hilbert space. For measurement of any dynamical variable, you see how the dynamical variable is as a function of x and p classically. You change the x and p to x and p and you find this operator, and then you can state about the probability of finding the state in any eigenvalue omega, and the probability is given by this. Then we talked about the relativeness of this probability, then we talked about a lot of things, then we talked about the complications. The complications where this might falter, the degenerate case, the continuous case, and the case where the omega might not be a function directly. Sorry, omega might not have a classical analog at the first place. So we talked about all these things, but please try to understand all these things we have been talking about before doing a measurement. Before doing a measurement, the probabilities that we calculated, I have been saying it like 3-4 times now. The probabilities that we are calculating, those probabilities are before we have actually done the measurement on the state. Why? Because after you have done the measurement on the state, it collapses to any one of the eigenvalues. Yes, and which eigenvalue it will collapse to, the probability that it will collapse to jth eigenvalue is given by p omega j that we just calculated before the measurement. Cool? Clear? Let's now talk something, let's not talk a bit about measurement. Like what is measurement, how do we do measurements and all that. So, Does everyone agree with this? Till now? Is this fine? This is a state that you can always write it like this. Now I am saying the measurement collapses the state to some eigenvalue. Now there is this concept of an ideal quantum measurement. Now what is an ideal quantum measurement? An ideal quantum measurement states that if you are measuring a dynamical variable and the state of the system is an eigenstate of that same dynamical variable, then it will keep the state intact. As you can see, this is just an eigenvalue equation. P is an operator, P is an eigenvector of it, P is an eigenvalue, this is an eigenvalue. There's so many P's here, whatever. So this is an ideal quantum measurement. Why is it ideal? Because you are taking a vector, you are taking a state that is initially taking a state that is an eigenvector of the operator itself, and you are getting the same operator, same state. So the state is intact, kept intact. This might not always be the case, but the measurements that we have been talking about all through this time, all these measurements are ideal quantum measurements. So we assume that there are some, okay, so there is a process of how you can actually make an ideal quantum measurement of momentum. There's a process. Suppose you have an electron and you use Compton scattering and you take the momentum of the photon that you are using for the Compton scattering to be very negligible. So there's a process in which you make the state unperturbed, like undisturbed. Anyways, we won't talk about that. We will rather say that for every variable, we can construct an ideal quantum measurement. We'll assume that for every variable, there is some kind of a measurement technique that we can adopt, such that if I am doing that measurement technique on an eigenstate of itself, then it will keep it intact. It is very important that I am making this measurement on the same eigenstate, like the same eigenvalue. Why I am saying so? Suppose you have a momentum eigenvalue and you perform an ideal quantum measurement of position on it. So how will you determine that? Does this make sense? Yes. Yeah. By that I mean that the initial state of the particle that you have, that you chose to be one of the eigenstates of the variable.
It's not superposed, it's not a superposed, it's one state.
Yeah. Yes, exactly. Precisely. It is one eigenstate instead of a superposition. But suppose you have one eigenstate of momentum, but you apply an ideal quantum measurement of position on it. Will that change the state? Yes, it will.
Yes.
Exactly. Because P, you can write it like this. And if you operate, you can convince yourself that it will be something different. Okay, suppose you have your initial state like this. Suppose you have your initial state like this. As you can see, I have written it omega 1 and omega 2. Why? Because these are degenerate. These have the same eigenvalue omega. Just to label it differently, I have labeled it with a different one more index 1 and 2. Right? So suppose I have an initial state like this and I perform a measurement. So what is the probability that okay, forget about probability. Suppose I perform a measurement and I have this state, I measure omega, and suppose I get this. Any state, I measure omega, I get this. My claim is this state collapses to this. This is the projection operator of psi on this omega by omega psi. This is just a normalization. Is this intuitively correct? Can you understand this thing? This psi,
If omega is yeah.
yeah, like forget about this for a moment.
What would P omega be here? Because there are two states, right?
Which one? This one?
Yeah, what would the
Exactly. That I just said.
the plane one?
Huh? Yeah, the plain one. Yes, exactly. But like this is true for even for non-degenerate case, right? You have a state psi, you measure this thing, you are getting this. My claim is, if on measurement you are getting this thing, then the state collapses from psi to this. Is this understandable? Why? Because this is taking the projection of psi from psi that was in some n-dimensional space to that subspace.
That is just to renormalize, right?
Exactly. This is just to normalize. Clear? Now tell me this thing. If you agree with this, that the state collapses from this to this, tell me if I have a initial state like this, and I am saying that okay, I measured this state, and that state collapsed and gave me an eigenvalue this. Tell me what will be the state after measurement.
Repeat it.
You have a state like this.
Yes.
It is degenerate in omega. You apply, you do a measurement,
Yeah.
actual measurement, not some probabilistic shit. You do an actual measurement, and you find this is the value that you are getting. Tell me after getting the value, after doing the measurement,
1 by root 2 omega 1 omega 1 plus omega.
Yeah.
precisely. Did everyone understand? No.
Probability is 1 by it's a temporal that. It is the mathematics.
What? This thing?
Yeah.
This thing is completely intuitive.
No,
This,
I'm saying from where we get that, right?
yeah, if you just plug it in, you will get it. You want me to do it?
No, it's fine.
Okay, I'll just give you this hint. This is
Eastern norm.
right. This is this. You apply omega. You apply psi. You'll get it. Cool. Fine. Now, this is saying that okay, I knew my initial state was precisely of this form.
Yeah.
If my initial psi was not known, Suppose you had a psi, some psi. So this is my omega 1, this is my omega 2. Sorry. Saying this means we knew exactly how the vector looked in this three-dimensional space. But suppose we didn't know a priori what that wave function looked like before doing the measurement. Can we say something that what the state will look like after doing the measurement, provided I told you that I got this value? Did you get my question clear? This is, I knew this state psi, then I made a measurement omega, I saw that I am getting this value for that measurement. I asked you, after doing that measurement, what will be the state wave function, the state vector of the thing? And you said that this will be the case. Now I am saying, I don't know the initial state. I don't know what psi was initially. I just know psi was something. Psi was some vector in this three-dimensional space, somewhere. And I made that measurement omega, and I found out this. Can you say something about the state?
Something, yes.
Yes, tell me what you can say.
The ratio of the coefficients earlier, like in the previous state and in the post measurement state will be the same for omega 1 and omega 2, and they will be just divided by the.
Exactly. You can say something for the omega 1 and omega 2, but not something for the omega 3, right?
That will be 0.
Yes, because that is the what?
Initial state is coefficient 0.
The initial state does not have to be 0.
It's coefficient in the post.
Yes. That is precisely 0. So that is the point that I am trying to make. That
It's only for degenerate cases we can inform.
that you have a random vector like this, you didn't know what it was initially. But once you have made the measurement, and once you know that the measurement value is omega, so now you know that after measurement the state is somewhere here on this plane.
Yes.
Is this clear? Because now you know that it should be on this plane, right? Because you have made the measurement and you got omega. So if you got omega, then the final state should be somewhere in this plane, because this is the plane. Any vector on this plane will have the eigenvalue omega. Clear? So even if you didn't know the state at the beginning, you can fix it to some constants, up to some constants like this. And obviously you need to normalize it. This is the state post measurement. Provided I told you that the measurement gave me this value. Because this information made you realize that okay, after measurement this state will be somewhere. Clear? Okay. Tell me something. I have a state. I measured it. The state collapsed. Right? Everyone. This is a very simple question. The state collapsed. But throughout, I have been talking about probabilities, statistics, averages. How am I getting a probability if the state is like collapsing? I have already answered it in the beginning. Like I was supposed to tell it now, but I have already answered it in the beginning. Suppose you have a state. Let me just do it, right? Suppose you have a state. You measure this. You measure it. You measure it using this. It collapses to what? Tell me. Some eigenvalue of omega. Great. So let that be omega I. And you get the state to be omega I. Right? But if you have to actually test this theory using like if the probabilities that we have been calculating are correct or not. You would have to find probabilities. And probabilities means multiple measurements. How are you doing multiple measurements here?
Based on the state sample.
We have to take copies of the state. So the average that you guys know about, okay, this is a measurement, I measured it once, I measured it twice, I measured it thrice, I measured it n times, and then I divide by n. That is called normal averaging, time average or something. And this kind of an average is called the ensemble average. And this is where ensemble comes from. So this is called ensemble averaging. What ensemble means means the exactly same copy of the state. So you take state psi, you make exactly same copies, n copies of them, and you measure it. You measure it with omega. Suppose if we do, you have psi, you make psi. How do you make? I don't know. You just make. You make n copies of it. Yeah, you just make it.
Is it actually feasible and can be used?
How do we know we have made identical?
No idea. I genuinely don't know.
How do you know we are?
Okay, theoretically you can always say that, okay, let me have identical copies of psi. Yeah, but experimentally, how do you ensure that it is the same? I have no idea. I have no clue. Genuinely, I have no clue. So you have n copies of them. You measure with omega. Suppose this collapses to omega 1. Again you measure with omega. It collapses to omega 2. Again you collapse to omega 1. So on and so forth. My claim is, if the probability of measuring omega 1 was 1 by 3, then n by 3 of them would collapse to omega 1. Approximately. And yes, and 2n by 3 will approximately collapse to omega 2. Now, as you increase n to infinity, this will exactly be n by 3 and 2n by 3. So, if you have infinite copies of the same state psi and you measure them one by one, like you not one by one, sorry, you measure them parallelly. If you measure those infinite copies parallelly and you have these values, then n by 3 of them will be omega 1, 2n by 3 of them will be omega 2. This kind of an averaging is called an ensemble averaging. And this collection, this same collection is called an ensemble. Now this notion, name drop. Okay, this fine. This notion of an ensemble average is there in classical mechanics as well. And here you see in quantum mechanics as well. I won't extend much, don't worry, just a few more minutes. It's in quantum mechanics as well. There are some difference between the ensemble in classical mechanics and in quantum mechanics. And I will explain you that precisely using a small example. And probably we will end up today for that. Fine? Yeah, we'll end for today. So the example is, suppose you have a die, 6-phase die. Tell me whatever I am writing it, that is correct or not. Fine. This is like just writing the things of a die as this. Cool? Cool. Now what are the similarities of the classical ensemble and the quantum ensemble? Point number 1. The state is described by some probability function P of n. Oh, sorry. I haven't even described the process properly. So the process is
that's a
That's just some constant.
Just I times bracket like a 10 omega. That is
Bra I omega I get
That's
right.
CI, that's CI.
That's CI. That's CI.
It's a constant.
Okay, let me. I didn't. Okay, I didn't explain the experiment properly. So you have a dice. You roll it. Okay, no, you have a dice. You cover it with something, with some cover, and you roll it, and you open it. That psi is the state of the system before you are opening. Cool. Now in classical ensemble, what you will do? You will consider n copies of this dice and mug thing. You have dice and a mug, and you consider n copies of this, and you do the same measurement. Similarly, in quantum mechanics, you will do the same thing. You will consider an ensemble of systems. Now, my claim is the ensemble of systems that you considered in classical is very different than the one that you considered in quantum mechanics, and that is the point that I'm trying to say. Now, how they are similar? They are similar because both of them will be probability function given by some function before the mug is given.
How do you look at verification variable?
Did you guys understand this? These CIs are the weights that it might be okay, the dice might be in 1 or 2 or 3, whatever. The weights can be determined anyhow. But CIs are the weights. And this En is the probability that it is in n state, like the phase, nth phase. So in both classical and quantum ensemble averaging, this is true that there lies a probability function before measuring the mug. Before you are lifting the mug, there lies some function that says that okay, your dice should be in this state. Right? Right. Even in quantum mechanics and in classical mechanics, in both cases, you have a probability that says that the dice should be in some state. Does everyone agree? Cool. Does everyone agree?
yeah.
In both cases, consider this like a non-degenerate spectrum in quantum mechanics, like where you had discrete points that it could take.
Yes.
Take a moment to look at this. Did everyone understand this? As soon as you are lifting the mug, the probability function that you had before, that is just collapsing to delta n3 in both the cases. Because once you are lifting the mug, you are seeing that okay, by 3 I mean if it is in state like phase 3. So if you are lifting the mug and you see the dice is in 3, then the dice is in 3. So after the measurement, the probability function is delta n3 anyways in both the cases. Did everyone understand? This side is everyone getting everything? Class 12 statistics. Probability. Clear? Did everyone get it? Fourth point. Normal probability.
What is NNPA?
N is the number of ensembles that you have, capital N. And N is the face, the dice face.
Okay.
Clear? So these are same in both classical and quantum ensembles.
result n also this value.
Did you understand? Cool. Matlab, by saying this, I mean that you have an ensemble and you found out what is the like how many of them will have one on the face that will be given by n times this one. The same thing that I was talking about, that if the probability of getting omega 1 is 1 by 3, how many of the ensembles will have omega 1 to n by 3? Clear? If the probability of getting small n is Pn, how many of the ensembles will give me a result in NPN? Clear?
Of n.
This is same for both classical and quantum.
Okay.
Right? Then what is the difference? The differences are these. In classical case, you can at least theoretically predict what will be the phase of the dice. Like suppose you know the coefficient of restitution, suppose you know the density of the material, the mass, viscosity, everything you know. Like every dynamical variable you know. So in principle it is deterministic. Classical mechanics is deterministic. So you can determine with exact precision what phase my dice will show. Right? Is there any?
We are just assuming, right, that in quantum mechanics there is like pure chance.
Not actually deterministic.
Yeah.
That's
We are assuming like that is a postulate, right?
What?
That in quantum systems
the probability is
there
actually
is
not
just
deterministic.
purely probability.
It's not like that.
There is no determinism. Like there is.
Yeah, that's the postulate of the theory. That's the postulate of the theory at the first place. That you can't deterministically find out that what state it is in beforehand. Before the mug is lifted, you have a dice, you shake it, you haven't lifted the mug. Before the mug is lifted, if you knew all classical things, you knew viscosity, you knew this, that, everything, you could in principle calculate that what state it is in. But in quantum mechanics, you couldn't.
What if quantum mechanical effects come into the die?
Ignore that. Yeah. So in principle, you could find out what phase it is in. But in quantum mechanics, unless and until you make that measurement, that dice is in a superposition of all 6 phases. Clear? Yes.
I suppose concept is a random question at the same time to do this. Is it because of that you can't determine the state, or like, suppose you could know position, then you will determine the state of it.
No, the point here that I am talking about, that you don't know the state a priori measurement. That has nothing to do with Heisenberg uncertainty. Heisenberg uncertainty principle comes for 2 variables that are canonically conjugate to each other. That is a completely different. Here the point is, unless and until I am making a measurement, the state will be in a superposition of all possibles.
Suppose you did
Okay, we'll come to this discussion later. Just let me complete, because we're running out of time. We're already out of time. Okay, cool. So you can actually predict if it was n equals to 3, then in classical case, just before making the measurement and just after making the measurement, it was at the same thing, right? Right? Just before you are lifting the container and just after you are lifting the container, it should be in the same state. In classical. Okay. This, you are shaking it, you made it to rest, now you are about to open it. Just before you are opening it, it was still in n equals to 3. Yeah. But in quantum, it was not. In quantum, it was not. Before you made that measurement, it was in an equal superposition of all the possible values of this measurement that you made. If this measurement that you are making is omega, then before you made that measurement, before you opened it out, it was in a linear superposition of all the
Yeah. Like instead of thinking about the lifting the lid thing, if we think that we are shaking the die and then throwing, like until it stops, after stopping it has a valve, but before stopping it, it not have a valve.
yeah, that's the thing. So if you are not giving a lid, then you are constantly measuring the system. You're constantly measuring the system. You are not letting the quantumness come in. You can make the quantumness come in by not looking at the system. It's their classical pop science Schrödinger's cat wala thing. And unless and until you measure it, it's a linear superposition of both the states. Exactly that thing.
Technically speaking,
Hmm.
the fact that the dice are already interacting with the air molecules around it, they are already getting measured. So it's not too
No,
very-
it's- But one thing is because like the
Understanding.
act of stopping the scrambling of the dice and the measurement of the dice are two separate things. Versus in quantum mechanical thing, the stopping of the superposition and measurement is the same.
Nah, those are different. In quantum mechanics, the measurement is defined by me opening the lid, not stopping of the die.
They are not getting is the same. Like the reason why we are not getting a superposition of it before lifting the lid is because it has already stopped rolling before, right? Basically. So that these two events of the thing stopping being in a superposition and us measuring it are two different things.
By event, I just mean me taking out the lid, because me taking out the lid is the only thing that I'm measuring on the system. It stopping by itself is not something that I'm measuring. It's not. I'm not interacting with the system. Did you get it? I'm not interacting. You had a question. And the third point is that if we had n monks and n dice, like basically if we had an ensemble of n of those systems, and if we found out that the probability fine, if we found out the probability is 1 by 6, what did it mean? It meant that out of all those n copies you had, n by 6 of them were cool. But in quantum mechanics, all of them before measurement were inside. After measurement, n by 3 of them did fall back to omega 1. But before measurement, all of them were inside. Did everyone get it? Yeah.
This follows from our postulate, right?
Yes, yes, yes.
So, how to, I think this is, how do we know that there isn't something else that is happening that we're not able to determine that is causing it? So essentially, I'm saying it has fallen to one state of it.
Yeah,
How
true,
do we know
true,
that?
true,
Because
true.
it's not very-
No, true. You are correct. These are the postulates that we are fixing. These are the things that we are taking as axioms and doing our theory.
From the possibility.
Postulates, yes. Okay, I'll take this question at the end because this is all too late. I'll just finish it up and then we can take questions. Cool. So, did you guys understand the process of ensemble averaging and why it is important and all these things? And how a classical ensemble is different from a quantum ensemble? Cool. Now, with this powerful ensemble that we have, we can, in principle, find out two more statistically important. This is a promise. This is the last thing that I am doing. Okay, two more things. This and this. I'm pretty sure Anshu Pandey has gone you through these things. So, but I don't think you did it in bracket notation, right? You didn't. So the expectation value of any operator omega.
Yeah.
What do you mean by the expectation value of any operator omega?
Like student were defended as
Okay, till now the only quantum mechanics you knew was UCI 11.
yes.
Now you know a lot of things. Now you know how quantum mechanics actually works. Tell me in those things. What do you mean by the expectation of omega? Omega is a physical variable. If I apply it on some size, some
measure
state,
it again and again, and the average of all the values
For all the
it will approach this.
exactly. Did everyone get it? We know the concept of ensemble averaging now. So now we can define what this expectation value means. In principle, it might be that none of your systems, none of your copies give me this value. It's saying, for example, the average number of pets in a household is 2.12. But you can't have 2.12 pets in any household, right? So it's the same thing. This expectation value might not be the observable for any time, but this is a statistical measure that tells me, okay, this might be the observable. So this expectation value is given exactly like a classical expectation, classical average is given. What is the definition of a classical average? Suppose you have a continuous function, the something, whatever is called, probability amplitude is given by P of x. What is the average?
XPX typical divided by X equal to X.
So here it will be just did people get it?
Yeah.
Everyone. Great. Now we know what P omega is. Look at your notes, you guys know. We have already defined P omega I to be the probability density, like this. Not the probability density, actually, here it's the probability itself. Like the probability density was, yes, that's right. Yeah. Now is it correct? Now it's correct, right? Because I took it as discrete points. So it should be a discrete sum, not an integral. So this is the probability density times omega. Now I will use my favorite thing that I have been doing. I will write this absolute value as psi star psi. So it will be, tell me, psi omega I times omega I psi omega I. Did people get it? Like I have been using it like n number of times, right? Cool. Now here, this is where the bracket notation of Dirac comes into play. In bracket notation, you can separate the bras and kits. Like this is an inner product, right? But you can always think of it as a multiplication of a bra psi and a kit omega. Because it is indeed a multiplication of a row vector and a column vector. It is indeed a multiplication of a row vector and a column vector. That is an inner product. So that is where the speciality of this Dirac notation comes. And I will use that very cleverly. I will put this thing here. So you have psi omega I, psi. Clear? Everyone? Tell me something. Omega I is an eigenvalue of capital Omega. Omega I is an eigenstate of capital Omega. So this, exactly. Now this is the beauty of the Dirac notation. Like these things you just found out. Now tell me this thing. What is this?
There's a probability of like projection.
You have a sum over I and you have a projection matrix here.
Yes. Yeah.
Tell me if this is correct.
Yes.
This is the thing that you know
Yes.
from UCI 1.
Yes.
This is the expectation value that you know from UCI 1.
Yes.
Cool. So you know expectation value.
No, he didn't.
It was a slide, I remember that slide. This is the same problem.
He must not use the notation at least. Like,
Notation was it was functionally.
yes, it was functionally should be the same. The function
Operator on the vector becomes
yes.
value into vector.
So what he did was the thing that was written here. He took the state.
and broke it down.
He took the state and he made a position, one-dimensional position space.
Yeah.
He took the projection on that one-dimensional position space and he made this function. The state in position basis.
Yes. Yes.
And he used that for here.
Ah,
But this
for any discrete.
this or this are not in any space. These are not in position space or momentum space or any space. These are abstract vectors. This is an abstract vector of the dynamical variable omega, that I agree. But these are not written in any space. These are not written in a position space or momentum space. No, these are abstract vectors. That's what I was talking about that time. To take it from here to there, what you did was you constructed a one-dimensional one-dimensional line of omegas, and at every omega you found out psi omega, and you said that okay, it will be a continuous function. Thoda, everyone. Great. So this is a much more powerful definition than what you did in Anshu Mendes course, because these are all abstract vectors. These cakes, brass, these are all abstract quantities. These are not written in any space. Once you write it in something, then it will be something. The last thing for the day, uncertainty. So what the expectation value tells you is the mean value of your probability density. But to express any probability density apart from the mean, one more good quantity is the fluctuation about the mean. How it is fluctuating about the mean, and that is the standard deviation. That standard deviation, as you all know, is given by this. So you have that variable, you have its mean, you find out the deviations from that mean, you square the deviations from the mean, you take the average of those squares and then you take the square root of them. Root means square. Root of mean of squares, of deviations. That is fluctuation. Right? So let's construct it for the quantum mechanics that we have been dealing with till now. So for quantum mechanics, this, I will not say you how this comes, because by now you should be able to see this by yourself. Is this correct? Guys, is this correct? Yes. Can everyone convince themselves that this is correct? The expectation value of something is Clear? If you are taking for continuous systems, this was for discrete, right? For continuous, what would be the case? You would have p omega minus right, omega minus this, right? So this is the thing that we will be having for continuous systems. Cool. So delta omega is just this. Did everyone understand these two things? Like, clear? These two are very important dynamical variables that we have. This is something that we discussed. This is any two operators if you have any two operators omega and lambda, you can sometimes find states like this. These are called the simultaneous eigenvectors or simultaneous eigenvectors of both omega and lambda. So if you have a simultaneous eigenvector like this, what I mean by it is, if you act this and if you act this, clear? Clear? Can you see this thing? Can you see that this is indeed correct from this? Fine. Now, if this is true for any this, then this is 0. If this is true for any state, then this is 0. So that means so for two dynamical observables like this, for which the commutator of them is 0, you can in principle have simultaneous eigenstates like this, such that you can so let's draw this same thing for a simultaneous eigenstate. So you have this, and now if omega and lambda have some simultaneous eigenstates, then what will happen? I apply omega, it will give me omega, but the state will be again I apply lambda, it will give me lambda, but the state will remain. Clear? This is only possible for
Wait. Yeah. Lambda omega.
Lambda omega.
क्या?
We applied lambda omega times omega lambda, right?
Just lambda omega. All the activities.
Yeah.
Cool? But this is not the case all the time, right? This need not be like omega lambda minus lambda omega need not be 0. So there are two other possibilities. One possibility is that omega lambda minus lambda omega is something non-zero all the time for every omega. This is one possibility, that the commutator is never 0, whatever you would take. For this kind of things, for this kind of variables, you can never find a simultaneous eigenstate. You can never find a complete simultaneous eigenstate. These are called canonically conjugate. One famous example, so this is what you were talking about that time. The question that you are asking, that this whether it will be possible for commutating or non-commutating stuff or not. So this will be possible for this will be possible for this is for the non-commutating case. If omega and lambda do commute, it will be the case. There is one more subtlety, pathological, that maybe yes, exactly. No, you might not have for all the eigenstates, but some it is 0. That is of no importance to us, genuinely, because that doesn't give any physical inference. But that is also a possibility. It might happen that this is not non-zero. I said that, so it might happen that omega like this is, you get my point, that this is 0 for some states but not for all. So with this, we complete the discussion of the first 3 postulates of quantum mechanics. I had prepared for the last postulate, I had prepared for the Schrodinger picture, the Heisenberg picture and all, but obviously I couldn't complete it in time. I would end today by just filling up these blanks, and then you can just go back home and absorb whatever we studied today. One thing I think all of you can agree, that now the way you would look at quantum mechanics is different than what you have been looking at UCI 101. This is completely different. So, Siraj is sitting there. Siraj must have taught you that state variables change with time according to what equation?
So we will first of all just unknown. I didn't see
What are the Hamilton's equations?
There are multiple.
I might make it wrong.
No,
Wait.
delta is a delta E, and it's a minus of the other one. Yeah.
Did I do the minus correct or did I swap
No,
it?
it's correct.
I always swap it. I swapped it, na? Yes. Cool. So these are the Hamilton's equations. You have x, you have p, you have a function called the Hamiltonian that is given by the Legendre transformation of the so you find out p dot x dot like that, and you find the system's dynamics through. So this is the fourth postulate. The first three postulates give you the idea about how quantum mechanics is in general. The fourth postulate gives you the idea about how a given state evolves under a Hamiltonian. Oh, there's a difference. This H is formed by taking H Can everyone see that? This H is formed by taking the classical Hamiltonian and just changing the x's to the x operators, p's to the p operators. Just like the omega that we did. So you have a special dynamical variable called the Hamiltonian, and that Hamiltonian you can it shows that any state evolves according to this, and this is the Schrodinger solution. So yeah, that's it.